In the fourth and final part of the lecture, we will discuss how to train machine learning models. We have already learned how to create, fit, and evaluate machine learning models in this lecture. But the question remains, how do we choose the best model for our data? Let's have a look at the example of polynomial regression. We have some noisy data from an unknown polynomial model, and the machine learning task is to recover this model. To do that, we can fit polynomial regression model, but how do we decide on the polynomial degree of this model? So not all the models will fit the data equally well. Some models will underfit the data. And when this happens, the model misses important trends in the data. There are systematic errors in the predictions, which is called bias. And this is a sign that there are too few parameters to be fitted in the model. On the other hand, some models will overfit the data. And when this happens, model will not generalize well to unseen data, and it will be driven by noise in the data. And this is a sign that there are too many parameters to be fitted in the model. And finally, some models will be just right. And when this happens, there will be no systematic errors. The errors will be random. The model will generalize well to new data, and we will have right number of parameters to be fitted. So let's have a closer look at polynomial regression. We have m+1 free parameters, which are these weights w for the polynomial with degree m. So you can see that the polynomial degree m actually defines the number of parameters of the model and therefore its complexity. And this polynomial degree is also called hyperparameter of the model. So let's have a look how the complexity of the polynomial model looks in a fit of polynomial regression. So if we look at the polynomial regression of degree 1, which is a linear regression, what do you think? Is this linear model underfitting, overfitting, or is it just right? So this linear model, is underfitting the data. It is because we see that it misses important trends and there are systematic errors. It doesn't quite get this curved shape of the data that we can see. What about polynomial model of degree 20? Is it underfitting, overfitting, or just right? So this model is overfitting, and we can see that it varies too much. So it actually fits the noise in the data. And finally, what about the polynomial model of degree 2? So this model is just right. We can see that it nicely captures the trend in the data, but it's not affected by the noise in the data. So from this example, you can see that choosing a model of the correct complexity will prevent underfitting or overfitting. Now the question is, how can we choose the right model quantitatively? So because we have a polynomial regression task, we can evaluate R2 score for different polynomial degrees m. So far, we have evaluated R2 score on the same samples that were used in training. But if we do that, you can see that R2 score will increase with increasing polynomial degree. So it will always increase with increased complexity of the model. So we cannot really identify overfitting. So to identify overfitting, we need another set, which is called validation set. And it's very important that samples of this set are not used for training or for the fitting of the model. So we can calculate R2 score on validation set. And from this trend here, we can see that we get the highest score for a polynomial degree 2. And then when we increase the polynomial degree, so we increase the complexity of the model, the R2 score will start decreasing. And this is a sign that we overfitted the model. So you can see that using validation set, we can find the optimal hyperparameters. Usually, we will also need a third set of data. And this is called a test set, and is important that the samples in the test set are not used for fitting or validation. And we calculate the R2 score on test set only on our final model, so the one that we chosen during validation. And so it's for us, it's the second degree polynomial. And for this particular example, we achieved R2 score 0.88, which is quite good. So sometimes we would not like to exclude two sets of data from training because this decreases the quality of the model. So instead, we can use an approach that is called cross-validation. So we will exclude the test set as before, but rather than excluding validation set, we will split the remaining data into k equals groups that are also called folds. And now we will train the model k times, and each time we will have a different validation set. So different group will be chosen for the validation set, and remaining k minus 1 groups will be used as training set. And then we choose the hyperparameters with the best average performance over the k validation sets. And this diagram shows an example of 5-fold cross-validation. So if we fit models to different training samples, these models will vary from each other. And we can see an example of that in this plot. So let's look at the first example, a linear fit. So the black thick line shows the true underlying model, and the thin green lines show different models fitted to different samples, but these are all linear models, so same type of model, polynomial degree 1. And the red thick line shows the average of these different models. Now, by comparing these models, we can recognize 3 types of errors. So first type of error is bias. And this is the error between average predicted values and the true model. So here, this is our true model, and it has this nice quadratic curve shape. And our average predicted model is linear, so we have systematic error here. So we have high bias in this case. When we look at polynomial degree 2 and 20, we see that the true model and average model are very close to each other, so we have low bias. Second type of error is called variance, and this is the variance of values predicted by different models. So you can see that in case of linear and quadratic fit, the models don't vary so much from each other, so variance is low in both of these cases. But for polynomial degree 20, we have large variance. You can see that models vary from each other, so we call it high variance. And obviously, the models with low bias and low variance are the optimal models. There is a third type of error as well, and this is called noise. And this is the error between the sample target values and the true model. So this is a type of error that we cannot remove from the data, from the fit, because this noise is present in the data. But if we fit the model really well, then the residual error should be equal to the noise level. Now I would like to give the overview of most important scikit-learn functions for training machine learning models. The first one is called train test split, and this function splits the data set into training set and test set. So you can see here that it splits both the feature matrix and the output vector. And a parameter test size gives us the option to choose the size of the test set, and 0.2 means 20% of the data set will become a test set. The next function that I want to show you is called cross-val score. And this function calculates a cross-validated score. So in case of regression, it will be R2 score. So you can see that input parameters are model and the, again, feature matrix and output vector, but we will always input the training set into this function. We will also choose the number of folds, which is 5 in this case, and they are chosen by setting parameter CV. And this function will return an array of scores, one for each fold, and we can print out the average of these scores. We can see here we got 0.86. And then finally, we can calculate the performance of the model on test set. So we already know how to calculate performance of the fitted model. It's a model.score, but the important thing to realize that we fit the model to the training set and calculate the performance on the test set. Now, a very important scikit-learn function for choosing the best model is grid search CV. This function will use cross-validation to search through a set of models and give us the one with the best cross-validated score. So the models will be chosen by first choosing the family of the models and then giving the hyperparameter grid. And we can also choose the number of folds. And then when we run the function fit, this grid search CV object will loop through all the different hyperparameter settings. And for each of these settings, it will perform cross-validation and calculate the average score. Using cross-validation, note that it is always fitted on training set. And then after the search is done, we can access the best model through the parameter of the grid search that is called best estimator. And this will be the model with the highest average cross-validated score. The final bit of scikit-learn knowledge I want to give you is how we create polynomial regression in scikit-learn. So there is no dedicated model in scikit-learn for polynomial regression. Instead, we have to do it in 2 steps. The first step is polynomial feature transformation. So if we just look at the univariate polynomial regression, so that means we have just one feature x, then this polynomial feature transformation will transform this feature x into m+1 polynomial features. So they will be 1, x, x squared, and so on. And you can see that this object in scikit-learn is called polynomial features, and we can choose the polynomial degree. And the original feature matrix X is transformed to the polynomial feature matrix using function fit transform. Then the next step is to perform a multivariate linear regression. So we already know how to fit linear regression model. So there are two differences to what we've done before. First of all, when we create the object, we choose not to fit the intercept. So we set fit intercept equals to false. And I reflected this in this equation by putting feature x0 next to the first coefficient w0. That means we have no intercept, but this intercept will actually be there because we created feature 1 here. So that will effectively create an intercept for us. That's why we don't want a second one. And the second difference that we will fit the model to the transform features x poly. And you can see that if we call these steps one after another, it means that we will set all the features xj in multivariate linear regression in this equation here to the polynomial features x to the power of j, which have been created here. And then the combined equation will give us the equation of polynomial regression. So to summarize, we will train machine learning models by first splitting the data into training set and test set. Then in the second step, we will tune hyperparameters of the model using cross-validation. And in the third step, we will evaluate the performance on the test set. So the Jupyter notebook training models in scikit-learn will give you detailed guidance on how to train models in scikit-learn. And this is part of the tutorial, so not the lecture. You will do that during the tutorial. So you will learn all the details, and there are some activities for you as well. And then at the end of this notebook, there is exercise 5. In which you will recover polynomial model from the noisy data. The solution to exercise 5 is available as a video from Kids. The tutorial also contains optional resources. There are 2 Jupyter notebooks, one to learn plotting with Matplotlib, and the second one to learn data manipulation with pandas. Even though these notebooks are optional, please do solve the exercises in these notebooks, but you can do that in your own pace and time. And now is the time to test your knowledge. We will do that using a quiz on Kids. This quiz is called Training Machine Learning Models, and it covers the part 4 of this lecture. Please do not forget to submit the answer to the quizzes. It's mandatory, and we will monitor your attendance through the submission of your quiz answers. So this is the end of the lecture material for this week. You still will do the tutorial, of course, and the next week we will learn how to train various linear and nonlinear regression models in scikit-learn.